need surface area in my job.
Well, maybe just in living. When you go to paint a house or put siding on it or something, that's
I'll let my
surface area.
dad do that.
That's surface area. He's not gonna be around forever.
My sister is.
Forever. No one's forever.
I'd rather do that than do all of that.
There are other ways, but there are ways that
Like I've never
you think about it and figure out, like I'm trying to figure out what the cost will be if I want to do flooring. How much might it cost? So I'm figuring.
Depends on what floor you get.
I know, but I need to know how many square feet I need to.
Changes your plans for your house.
That you still have to figure.
Oh. So they'll tell you how much your house
You actually
is.
sit there like, you guys are lazy. Okay, all right, as far as shape, we have a pyramid, a cone, and a sphere to add to our surface areas today. So you should find section 10.5, and there's a little bit of 10.8 that's mentioned with it, because they put the sphere in section 10.8, surface area and volume. So we're gonna pull the surface area part from that section and then later do the volume part. So a bit of vocabulary related to pyramids and cones and then spheres, but also their surface area. So on a pyramid, remember the bottom of the pyramid was a polygon of some shape, and then there was a vertex that all those triangles come up to meet at. So the vertex is the point opposite the base. If it's a regular pyramid, these triangles are all congruent because this center point goes directly up from the center of the base. And that's going to probably be important to you as you are trying to do some calculations. If it's a regular pyramid, which are typically going to be the ones that we're working with, regular pyramids, that perpendicular goes straight up to the point. Let's see, I have some skeleton type of pyramids in here. Different ones. And so comparing the height that I'm talking about is this metal one. That's perpendicular. Is that the same length as this red one or this green one? No. There are right triangles going on, and so at times we'll need to do some Pythagorean theorem to find a missing measurement if it's not given. So we'll pull those out as we do those. Okay, regular pyramids, it's nice straight up. Non-regular, or we might call these from yesterday oblique pyramids, where it's slanted off to the side. Again, that point doesn't go directly perpendicular up. A non-regular might also have a base that's not a regular parallelogram or regular polygon. It might be like a rectangle base. Yes.
Is there only one vertex in that?
Actually, no. If we were counting vertices, faces, edges, we would be counting all of them. This one, that's why I like the resources that call this the apex rather than just the vertex. So when it's talking about the vertex of the pyramid, they're talking about this one, but there are 1, 2, 3, 4, 5, 6, 7 total vertices if we're counting them, which is kind of confusing. All right, any other clarifying things? See, on this non-regular one, not all these triangles are congruent. This one's actually not going to be as tall as this long one. So when we try and find surface area, it's a lot easier to find the surface area of a regular pyramid because all those triangles are identical. If you're trying to find the surface area on one that's not regular, you have to maybe think of every triangle separately and find its measurements. So we're going to stick to the regular ones. I think if you get enough of an idea of surface area, you could try those other ones if you need them. So on the pyramids, there is an altitude, which is the perpendicular, but there's also what's called a slant height. The slant height is the distance from the vertex to the midpoint of the edge of a base. So if we go from this vertex to the midpoint of this edge, that is referred to as the slant height. Pulling my model here, can you tell which one that is? Green, red, or metal? The one that goes to the midpoint of the side is the red. this one is the slant height. The metal one is the altitude. If you can kind of see or picture, there's a right triangle. The metal goes to the center of the base. So then half of that, I guess that's the apothem of the base. And the red makes a right triangle. That apothem and the metal are your right angles, or those are your legs. And the red one's the hypotenuse. You visualize that correctly? So that's the relationship. The slant height is always a little bit longer, or is longer, than the metal one, because that's the hypotenuse of that right triangle as opposed to the leg. So there are formulas we're going to use that have a slant height, and then there's some that we use that use the perpendicular height. So the slant height goes to the midpoint of the side. It actually is perpendicular to that side. So there's another right triangle that would be formed also. Lots of good stuff that could be used depending upon what we need. Okay, to do surface area of a pyramid, how many bases are there? There's one. What shape is it? Depends. Yeah, it could be anything. It could be a square-based pyramid. Those are probably going to be some of the easier ones, and that's what's pictured up there. But we also could have a triangle base to it. You could have, I don't know if I grabbed everything. I had hexagons and pentagons. I guess I put those back on the shelf. This one's not exactly the pyramid, but the hexagon base, one of the pyramid part of it would work. Otherwise, I put them on my shelf over there. So we will have one base to figure the area of. How do you figure it? Depends what shape it is. Okay, then you've got all these triangles. And I took those 4 triangles and peeled them off here to put them in one long strip so that we can develop what the formula is. So how do you find the area of one of those triangles? We'll call S the base. That's the length of the side. In this shape, all the sides are the same. Actually, in any regular pyramid, all the edges on the bottom will be the same because the bottom is a regular whatever, hexagon, pentagon. The L, is that the slant height or the altitude? That's the slant height. So it's the height of that face. So if we take 1/2, because it's a triangle, the length of that base times its height, which is the slant height on the pyramid, that would be the area of one triangle. Then we have to multiply by how many triangles there are. In this case, 4. If I would say in general, multiply by the number of triangles, what does S times N really give you? The length of S times the number of sides. That would give you the perimeter. So we can take 1/2 of the perimeter times the slant height to get the area of all those triangles. That would be the lateral area of a pyramid. So then if you would add on to that the base area, that would be the total surface area of the pyramid. Does that make sense? All right, so your formulas are, for a pyramid, if P is the perimeter and L is the slant height, the lateral area is 1/2 times the perimeter times the slant height. If you get mixed up, just find the area of one of those triangles, take it times how many triangles there are. Then surface area would be that same lateral area plus only one base area instead of 2. So look on my wall, where am I at on the posters? They're over here. Which one is today? The second poster. Okay. So the 1/2 perimeter times slant, and then one base plus perimeter times slant, those are your pyramids. Let's try some calculations. Find the lateral area and then surface area of a regular square pyramid. It might help to draw yourself a pyramid. The base edge is 14, the slant height is 25. And you're going to find the lateral area, then surface area. I usually do the slant pipe like on the side one instead of the one that comes straight at me. Get the dasher in there. So your lateral area, all of those triangles would be 1/2 perimeter times slant pipe. What's the perimeter of the base? It says it's a square pyramid, so that should clarify every edge is 14. So 14, 14, 14, 14, 56. And the slant height is 25. That multiplies to be how much? 700 square centimeters. Surface area would be that same thing, plus how many bases? 1 base. And the base is a square, which is going to be one of our easiest to do. 14 times 14, so 196. It looks like my surface area is 896 square centimeters. Follow-up clarification? Okay, if not, let's try another one. Okay, let's try a regular hexagonal pyramid. Have to work a little bit more on the base when you get there. But the first part probably will be easy. Lateral area, I think they gave you everything you would need. Find the lateral area. Perimeter was 60. Slant height, that is the 16. Got to make sure where it comes to. So that multiplies to be 480. Okay. Now for surface area, we need that, 480, plus 1 base. Okay, so let's work on the base. What shape? Hexagon, regular hexagon. How do we do regular polygons? 1/2 apothem times perimeter. Perimeter you already figured out was 60. We've got to work on the apothem. So how did we do this last chapter? What? Okay, maybe sine, cosine, or tangent. What angle? You got your central angle of 60 degrees. And then you split it 30, 60, 90. I think it's going to be faster if we know our 30, 60, 90. Because this edge was 10, right? So the short leg would be 5. And I'm interested in the long leg, 5 times square root of 3. I'm going to leave it as square root of 3 at the moment. 5 times square root of 3. So then when I multiply, without going to decimal yet, 150 times the square root of 3 is my base area. So now let's go decimal. 480 plus 150 times the square root of 3 ends up plus 739.8. Square inches. Now the directions really didn't say go to decimal, so it's very possible that our textbook would just be doing the 480 plus 150 times the square root of 3. That would be the exact surface area. Before I get rid of any of that, questions to clarify? So you can see how last chapter comes back. Might have to use sine, cosine, tangent, but that was our 30, 60, 90 triangle. Anything more? Okay. Make sure you got the right answer. That's what we had. All right, let's try one more pyramid before we go to a different shape. Find the lateral area and surface area of a regular triangular pyramid with a base edge length 6 and a slant height of 10. So the base is a regular triangle, in other words, equilateral and equiangular. Lateral area and surface area. We got the lateral area figured. I think everything was there for that. The perimeter of the base, if it's a triangle base and each edge is 6, 3 6s, 18 was your perimeter. The slant height was 10, so half of 180 should have been 90 square feet. Okay, got that part? Okay, then you're doing the base area. You're trying to find the area of this triangle to add on, right? Edges were 6. Probably, are you doing the total height or the apothem? If you're doing the total height, I think some of you were doing it that way. I'm going to think about angles here a second. What are the angles in the triangle? It was equilateral, so it's equiangular. So that angle, or this one also, all of them are 60. So I've got a 30, 60, 90 again. 3 times the square root of 3 is the total height for that triangle. So the area of this triangle is 1/2. What would I use for the base? 6. And then the height was 3 times the square root of 3. Without going to decimal yet, 18 times 1/2, 9 times the square root of 3. How many bases do I have? Just one on a pyramid. So surface area then is this 90 plus 9 square roots of 3. go decimal, we come up with 105.6 square feet, approximately. Raise your hand if you got it right. Raise your hand if I didn't give you enough time. All right. Okay, questions? No? Okay. Again, the pyramids, I think, are harder than the cones and the spheres. So if we're getting that, then we're off to a good start. Okay, cones. Let's go to the next shape. On a cone, there's a vertex. You asked me how many vertices on a pyramid. A cone actually has just that one vertex. So same thing about a vertex of a cone. There are right cones, there are oblique cones. When I look at the oblique cone, I think of a waffle cone. Because if you flip that over, it's not nice symmetrical, doesn't it? Kind of slant if you stack it on its side or on its top. So anyway, right cone and oblique cone. There are lateral edges, right edge, or right cone, oblique cone. There also is a perpendicular height and there's a slant height. The slant height on a cone would actually be right on that you draw when you make the cone. All of those, no matter where you put it to the edge, would be the same length. That axis is perpendicular. So on a right cone, you're going to have probably an easier triangle to see. There's your right angle, the radius, and the height would be the legs of a right triangle. The slant height is the hypotenuse of it. We'll probably have to find a missing measurement, like they'll give us the height, but we need the slant height, so there's a way we can find it. So how are we going to do the surface area? This part that goes around is kind of hard. If you remember when we did the net, I probably didn't have that much. I had more like half a circle. But it was part of a big circle that would wrap around to make the net when we looked at that. It's kind of hard to discover how to find that area. So here's how you do it. You take pi times the radius of the circle times the slant height, which is like the radius of that slanted part, if you would lay it flat. So pi times radius times slant height will give you this lateral area. Then if we add on to that the area of one circle, pi r squared, that would get you the area, surface area of the whole thing. All right, understand the formula. R is the radius, L is the slant height again. Let's have you try the lateral area and surface area of a right cone. Oblique cones are hard to do surface area. That would be more of a calculus type thing. Surface area and lateral area of a cone. The radius is 9, the slant height is 15. That would be pretty easy, wouldn't it? Let's go there. Let's go over this in terms of pi. So if you have something like 15 pi plus 2 pi, you can get 17 pi. So you can add together. Ready? your lateral area should have been pi times 9 times 15. If you just keep it in terms of pi, that was 135 pi per centimeter. Then add to that pi times 9 squared. So add on 81 more pi. So you get 216 pi square centimeter. Questions on that one? Easier than a pyramid. Okay, let's try another one. Find the lateral area and surface area of this cone. Careful. 15 is not the slant height. The perpendicular, you have to find the slant height. How? Take a look, I mentioned it a little bit ago. The diagram theorem can work, or if you recognize the triple. How many of you caught that? You knew that you had to find the slant height? Somebody did? Check with those around you for your answer. All right, the slant height was 17. The lateral area was 136 times pi. And the surface area was 200 times pi. Got it right? Questions on any? Okay. Anyone still need the screen? All right, so let's just talk about this one briefly instead of completely doing it. What are some things you need to come up with? Radius. Radius is what? Okay, so the radius is 8. Slant height would be what? 6, 8. Recognize the triple, 10. So watch for the correct measurements. So don't get tricked by having the perpendicular height and you really need the slant height. So watch for those. And again, diameter, you need the radius. All right. Advance. Okay. There are some problems, but you didn't have too many questions on your homework today. Did you figure out what happens to the surface area? Like if you're doubling every measurement, does the surface area double? Quadruples, because surface area is using 2 dimensions. So if you are changing the sides, if you're taking all the edges and dividing them all by 5, what's going to happen to the surface area? It's going to be divided by, not 10, 5 squared. 0.5 is what it would be divided by. Okay. So to show you that, I did calculate, and maybe this is what you did to come up with what was on your homework. It's a little bit hard to find, but 450 divided by 25 is 18, and 150 square roots of 3 divided by 25 is 6 square roots of 3. So you can try it. Going to decimal maybe wouldn't be the easiest to compare, but you can figure it out that way. So if the base edge, the slant height, if they're multiplied by 2/3, like all the way around, what's going to happen to the surface area? Multiplied by how much? 4/9. Because you're squaring the relationship because of both directions. And again, you can try it if you need to. To come up with it multiplied by 4/9, you would have to stay in fractions when you're comparing there. Okay, how about a composite figure before we throw in the spheres? What's that made out of? Cones. Are the two cones the same? Not exactly. They have the same circle, but one's longer than the other. What's the slant height on the one that's not given? 10. That was kind of the one that we had just a little bit ago. Okay, so I don't have two cones that are different with the same base, but this is kind of the shape that you got. So how are we finding the surface area? Do you want to think about just lateral areas, or do you want to continue find the surface area of both and then subtract? Let's try it the lateral area kind of way. Because what do you need of this green cone? Don't you just need its lateral area? Because we would be subtracting that anyway. And how about the other cone? Just lateral area? Okay, so rather than find the surface area of both and then subtract off the two circles, let's just leave the two bases out to start with. So do lateral area and lateral area. And just add it together and you're done.
Will the radiuses be the same?
The way that those are hooked together, yes, the radiuses are the same. Ready for an answer yet? Okay, I'm saying 132 pi. Left-hand cone was 72 pi. The right-hand cone was 60 pi. And we're just adding those together. We didn't have to subtract anything because we never added in the bases. Does that seem easier? So if you can think about that, maybe on surface areas could work better for you. Questions before I go on? Okay, another type of combination. I know these are not cones, but we could do the same thing with a cylinder and a cone. Find the surface area of that composite figure. Can you describe that to me so I know what to grab? What is it? And I think it's a cube actually. And then what else? With a pyramid. Right. Okay, taken out. Now these are solids, so how do I get it to go down in there? I have to take off this base, right? So I don't want that when I do the surface area. Now if I put that down inside there and leave it the way it is, it's closed on top. But it's supposed to be open. Right? Otherwise I can't go down into it. I need to take the bottom off of that. So I don't want this base either. that help you know what to do for the surface areas? What do you really want of the cube? You want the lateral area? Do you want any base? You want this base, don't you? But not the top one. So we could do lateral area plus one base. And how about the pyramid? What can I touch here? You want the whole surface area? Just the lateral area. Don't worry about that base, just leave it off. Okay. All right, so do we have everything we need? We don't have the slant height, do we? Okay, so that slant height, this would be, let's see, I'll draw it this way. We want the slant height figured out. What's this length going up? That's 2. This, can you imagine what that is from the center out? That's 1. So 1 squared plus 2 squared, 5. Square root of 5? It's not a 30, 60, 90. I just did Pythagorean theorem. Okay, so what did we say we need? On the cube, we need the lateral area and 1 base. Hey, every face on a cube is the same, isn't it? 2 by 2? So how big is, what's the area of 1 face? 2 by 2, 4. And how many of them do I need? 5. So what's that? 20. So the surface area was 20. That's for the open cube. That's all we needed, right? Those 5. Then we need the lateral area on the pyramid. So the pyramid, lateral area. Bad pyramid. Lateral area is just 1/2 times perimeter times slant. What's the perimeter of the pyramid? 2, 4, 6, 8. And the slant height, we calculated the square root of 5. 4 times the square root of 5. Are we going to add that to the 20 or subtract that from the 20? Is it a surface or is it gone? No, this is gone. That is there. The lateral area is there, right? You can touch it. Lateral area is there. Lateral area is here. We did never add on this base, so we don't have to subtract it all. So I'm coming up with 20 plus 4 times the square root of 5. Give me a thumbs up or down. Are you with me? Yeah, we are? Okay, kind of. So what you got to think of is, or the way that I'm having you think is, we took the top of this one off. So instead of 6 faces, we just needed 5. That's where we got the 20. 4 times 5. And then for this one, we just wanted the lateral area because the bottom we need to have open, otherwise it doesn't go down inside. All right, so what's that in decimal? I'm guessing my answer is in decimal. 28.9. So perhaps as you work through the assignment tonight, you would think of your, like, is it just lateral area or is it total surface area? We need to add the sphere onto it, and we can do some nice combinations with spheres and hemispheres. So what's a sphere? 3-dimensional shape, yep, it's a ball. So flip to, I think this, did I put it right after that? Okay. So the 10.8, a little bit of vocabulary. A sphere is a locus of points, so a collection of points, but it's in space, a fixed distance from a given point. The circle, it was just in plane, but now we're in space, so we're going 3-dimensional. So there is a center of a sphere. So there is going to be a radius of the sphere. Sometimes where you draw it, it looks different. That radius, this radius, those are all the same radius going to the edge of the sphere. But notice how they could look different based upon where they draw it. Yeah, it's just a different part of it. it looks different as far as drawing it on the picture, but it's really the same distance. So a center, a radius, there would be a diameter of a sphere, half of a sphere, hemisphere, and then a great circle. The great circle divides a sphere into two hemispheres. So when I pull this apart, that flat circle that would be right there, that is the great circle. In this one, I guess. But that is referred to as the great circle. The biggest circle that's possible, remember we were doing cross sections? You would do a cross section on a sphere, you get a circle. Right through the center is the biggest circle possible. If you would slice it closer to one end, you get circles, but they're smaller and smaller all the time. Okay, that great circle is actually important when we do surface area, because the surface area, to cover the surface of the sphere, it takes the same amount as 4 of these great circles. That's what the area is. How do you find the area of a circle? Pi r squared. So if I say you need 4 of them, multiply by 4, so 4 pi r squared is going to be the surface area of a sphere. How can I get you to visualize that? Here's the formula I just mentioned. One year we took the laces off of a softball. And it's not going to be perfect circles because have you ever tried to wrap a ball for a present or anything like that? Trying to get it flat is really impossible to do. You have to have so many little pieces. So it's not going to be a perfect circle when I take it off, but you can kind of visualize that would be the equivalent of the area of a circle. There's a second one, there's a third one, and a fourth one. Arranged correctly so that it covers it, but those are your 4 circles that would cover the surface of the sphere. So all you need to know is what the radius or diameter of the circle is, and you can figure what the surface area would be. Probably the easiest formula out of all of them. So what's the surface area of a sphere if the radius is 38? Just keep it in terms of pi. Do your order of operations correctly. Don't multiply by 4 before you square the radius. Radius squared times 4, and then times pi. But if you keep it in terms of pi, did you get 5,776 times pi? That would be 38 times 38 times 4. And then just put the times pi to keep it in terms of pi. Square centimeters because we're doing surface area. How about find the surface area of the sphere if the great circle has an area of 49 pi? Great circle has an area of 49 pi. What's the surface area of the sphere? I'm kind of curious how you worked through this one. How many of you took that and found the radius? Anybody take that, just times 4? See how you could just take that times 4? Because that's already giving you pi r squared. So we were about half and half on how you did that. So if you found the radius, it was 7, and then 196 pi square miles. All right, so that great circle. What's different about this one? What's that 50 supposed to be showing? Diameter. So be sure you would take a diameter and divide it to get the radius. Some of these numbers get big because of squaring, a 2-digit number. How many times pi? $2,500 times pi square centimeters. Right, so spheres are nice to do, I guess I had these kind, let me skip those, we talked about those earlier. Spheres are nice to do some combinations with, but typically you're not using a whole sphere, you're using a hemisphere. So let's think about, I guess this is kind of two different ways. If I take the sphere and pull it apart, it does not have a flat bottom to it, if I do it that way. If I cross-section it, it does have a flat bottom. So if you were just finding the surface area of a hemisphere by itself, you'd have to consider it having a flat bottom. But if we are doing combinations like up here, that hemisphere, it doesn't matter if it has a bottom or not. It's going to be sitting on top of the cylinder, so the bottom would be gone. How would you find the surface area of this hemisphere, the curved part of it? You could just do 2 pi r squared. So if you want to write that down for yourself. Hemisphere, if you're doing the curved part of it, not a flat bottom. So hemisphere on combo shapes, 2 pi r squared. Technically, if a hemisphere is by itself, it would be that plus 1 more circle. Okay, so how would we do the surface area of this composite figure that's up there? What parts of the cylinder do you want? Lateral area, 1 base, but not 2. And then for the top, we need 2 pi r squared for that curved hemisphere. Start calculating. So on. Make sure you're using the radius of 6. So for the cylinder, we said lateral area plus 1 flat circle base. Curved part, that hemisphere, 2 pi r squared. And then you had the hemisphere part. Let's see. Surface area of that, 2 pi r squared, we said. So that's 72 pi. All right, so you had the 108 pi for the lateral area, 36 pi for 1 circle base, and then 72 pi for the curved part, the hemisphere. And you get 216 pi square inches. Did we do it? No? What'd you goof up on? You didn't do the lateral area right? Got to look back. That was on yesterday's. So that was the 2 pi r h. No clarifying questions? Okay. combo to look at. Then we'll just click through and make sure I didn't forget something that was real important. There's the separate work for that one. Okay, how about this one? So what's that? Got to take a base off of the cylinder? Do I want a flat part on the hemisphere? No, otherwise it's not going to go down in there. So I just want it open, and it's going to go down inside here, right? So what do I want for surfaces? Cylinder, okay, one base, lateral area, and get the surface area of that. 2 pi r squared, just like we did when it was setting up. You subtract 2 pi r squared? No, it's a surface. Instead of going up, it's going down, but I can still touch that same curve thing. So realize that last problem we did, the way we found that surface area is the very same as the surface area we're doing right now. It would hold less. That's volume. But the surface area is the same. It would take as much to build this as it would to build it going up. That making sense? So I guess with that in mind, I don't think you have to completely calculate it, because I just did it on that last one. Unless you need to practice. So the lateral area, okay, I guess I did the hemisphere first, and then I've got the cylinder, lateral area, and the base. So the lateral area on the cylinder was pi times 3 times 5, 2 of those, I guess, 2 times that. The cylinder was pi r squared, we only wanted one of those bases. And then the hemisphere was half of a sphere, so only 2 pi r cubed, or pi r squared instead of 4. But when you added it up, it should have been 57 pi. Alright, so you can do all kinds of fun combinations. And we can do a hemisphere on top of a cone. We can do a cone on top of a cylinder. We have it going down inside. We can make a giant pill capsule. On that one, you could think of the 2 hemispheres together and do just the surface area of a sphere, and then the lateral area of the cylinder. So there's some neat combinations you can do. I'm sure you have a few on the assignment. Well, let me see if I forgot anything. I guess not. All right, I'll go back to that for you. Is that the one I was on? All right, the assignment, page 693 and 718. There's a couple problems that it asks for volume and surface area. You'll just do surface area. So just to clarify, it's page 693, 1 through 11, 15, 18, 48, 50, 52. Those will be the pyramids and cones, I think. Pyramids and cones. Watch out that you're using slant height, not perpendicular height. And then the spheres and hemispheres with combinations are on the second page. On 11, just do surface area. 12, just do surface area. It asks for volume also. We won't do that until tomorrow. So at the beginning of tomorrow, I do plan to give you a quiz with about 8 surface area problems. We'll do that at the beginning of class, like after our homework questions, because I don't want to go over the volume formulas right before you take the surface area quiz. That gets kind of confusing. But here are some problems to look through or some practice preparing for that quiz. All right, we do have some time. I don't want you to start just talking, so get to work.